Cool. And then we'll leave the room unmuted so people can also just yell questions from the room. That seems to work all right normally.
All right.
But we'll give it a few more minutes.
Yeah, sure.
We were early.
Oh, now we're at the top. And can you guys see the video, the Zoom video now that's partly in the screen that I'm sharing? I guess not, actually. Okay.
So here on Zoom, we only see your shared screen
Okay.
and our own heads. But then in the room, it looks like on the screen, they can see whoever's talking and your slides.
Okay. Okay, good. You'd think I'd have figured out this technology by now.
I mean, it's always slightly different everywhere. So
been enough practice. Yeah.
I've had panic moments where at the very end, then the sound didn't work and we had no idea why, and we had to abort everything. It's like panic when 10 people try to tell you how to do it at once. Cool.
I think that should be okay. Good.
Sometimes we swap the 940 camera around to face the audience. But I don't know that anyone's actually in there right now.
Yeah, it's hard to tell. I think at some point
nobody here. Probably was in the email. Nobody here.
My hand disappeared.
Yeah, so I was wondering, I mean, I'm in my office, I can go down. I wasn't sure where
maybe people are going to join from wherever they are.
Cool. Yeah, I sent
but you know our people. They always are doing things at the last minute.
It is the correct way to do it.
Yes, I always get things most efficiently done at the last minute. Not always as well done as it could be, but definitely, definitely more quickly.
Remember, we're being recorded, Mike, so careful.
Oh, shoot. Yeah.
Just kidding. Kathryn, I just saw also you finished from Columbia in 2011. I started in 13. So we just
just missed each other. Okay. Yeah, that's was a good place to go through.
Yeah. Who was your advisor? I don't actually know.
I worked with Jacqueline Van Gorkum.
That makes sense. Yeah.
But doing radio astronomy. So
yeah.
I don't know. I'm not going to say I learned the error of my ways, but I branched out.
It's always good.
There's not enough radio astronomy in the field of galaxies.
Yeah,
right. Doesn't it always seem like there's never enough radio data?
Radio data is a prized thing. It's going to get better with like all these Meerkat sort of things coming online in the south. Be good. The problem right now is, VLA can only go so far south, and then you've got all these instruments on the ELT, on the VLT that are.
Thank you for setting it up. Yeah, I can hang out and see if anyone comes.
It sounded like Kate entered the room.
Hi.
Yeah. Hi. We're just giving it a few minutes for people to show up.
Great. I'll mute us over here for now.
I think you can leave it on because then people can ask questions.
Can just shout them out. Okay.
Yeah, I can always mute if you get too rowdy in there. I have the host powers.
So, Kate, are people in there? I mean, again, I can come downstairs. I'm in my office.
There's no one here
I
yet.
can have coffee here. There what? Sorry, Kate.
There's no one here yet.
Mm-hmm. Lord joining.
Maybe it's a Zoom day after Thanksgiving.
Mm.
Right.
I'll go downstairs so that Kate is not alone. I'll be ready.
And maybe when you arrive there, we can start.
Yeah,
that should give people a little couple minutes.
Time. Okay.
Yeah. Sorry, Kathryn, maybe it was overkill to tell you to join 10 minutes early.
No, it's okay. It's always a very good idea to test the technology because when it doesn't work, then it's no fun for anybody. Still trying to figure out where I'm supposed to. I need a second monitor. I should have a more professional setup by now. So when you were at Columbia, who were you working with, Sarah?
I was with Kathryn Johnston and Mary Putman, actually. I kind of did the 2 first-year projects and worked with both, but not really. We were kind of overlapping in some of the papers, but I kind of did 2 separate topics, interacting dwarf galaxies with Mary, and then stellar streams with Kathryn.
Cool. Lots of stellar streams these days. I was just helping review the ESO proposals, and everybody's waiting for DR3 from Gaia.
Yeah, that's exciting. Very cool. Okay, I see Miriam coming into the room. Yay. So let's get started. Today we have Kathryn Kreckel from Heidelberg. And before we get started, I just want to remind people that from the 940 room, feel free to yell out questions throughout if you have any, and I'll be monitoring the Zoom questions. And we'll try to also interrupt you, Kathryn, especially if it's like something for logic flow, or if not, we can also wait till the end with questions. And the talk is being recorded, so you also have a chance to see it later on if you can't catch it right now. And then Mike will do the more scientific introduction. So take it away, Mike.
Yeah. So I don't know if I've ever actually met Kathryn. Maybe we have. That's always embarrassing if I don't remember. But I've been watching her work for a long time. She does a lot of work on gas in local galaxies, and she's, there's sort of a thing that happened over the last 10 or 20 years, which is we developed these really big samples of local galaxies and lots of their properties, big statistical samples that put like sort of the more focused galaxy observations of the past into context in a big statistical sense, but the individual observations weren't very detailed. And now I kind of feel like the galaxy community is bifurcating in a way where there's a certain set of people who are like doing that work of big samples and the population of galaxies out at high redshift, and just like pushing that back and looking at the evolution. And then Kathryn is part of a different group of people who are looking with, modern instrumentation in detail at the galaxies of the local universe, and trying to understand galaxies from very precise and detailed observations of a handful of galaxies, but again, with the modern instrumentation that we have. And she works a lot on gas phase metallicity, on star formation rates, on all these things that are important to the production of the galaxy itself. She's going to tell us about that today, and so I won't say anything more about it. Thanks.
Great. Thanks for the introduction. Yeah, so it's this, that's right, this local view of the galaxy as it grows. Breaks my heart a little that I can't be there in person, because as I was talking to Sarah, I was a grad student in New York City at Columbia. So I'm always sad to miss an opportunity to visit, but hopefully that will come up again soon. So in my talk, I want to show a little bit about what I've been working on and some early results from my research group in Heidelberg at the university, where we're studying the ISM in nearby galaxies. So this is the interstellar medium, which is the gas and the dust between the stars. And while the ISM is a small component by mass in a galaxy, it's really central to the cycling of baryons and the evolution of a galaxy. The physical conditions and the dynamics that are affecting the ISM can act to either trigger or suppress star formation. And the ionized component of the ISM in particular is tracing different sources of radiation and mechanical feedback and providing insights into the physical processes that are shaping the evolution of the galaxy disk. So with this beautiful 3-color image that you see here of a well-studied nearby galaxy, NGC 628, You see a familiar view of a typical spiral star-forming galaxy. But taking a multi-wavelength view to this galaxy gives us access to different phases of the ISM. So when we zoom out and look at the extended, so it's clear that the stellar component is playing an important role, shaped into these sort of spiral structures. But the stellar component is actually enclosed within an extended neutral atomic hydrogen gas disk that it goes well beyond what we typically think of as the disk in the stars. This material, this atomic gas, serves as a reservoir for the fueling future star formation. But actually, it's the denser molecular gas that's more centrally concentrated that correlates most directly with star formation. So if I zoom back in and we shift from this sort of bulk view of the molecular gas to spatially resolve the individual molecular clouds that are the sites of that next generation of star formation on sort of 100 parsec scales, what we can do now with ALMA, the majority of the emission is really located in these concrete structures. And if we compare the location of those molecular clouds with the locations of massive star formation, here traced by the H-alpha emission emitted due to the ionizing radiation from those massive stars, we can see that there's some correspondence between these two tracers. If I step back again, then you can see they're both tracing sort of generally the spiral structure in the disk, but there are some interesting differences in offsets. The correlation isn't perfect, so it shows that this connection between where you have the gas and where you have the star formation isn't completely trivial, and it has some dependence on the galaxy environment and the galaxy dynamics. If we look with even deeper observations at that ionized H-alpha emission, we see that those sites of massive star formation are ionizing not just a really small local bubble of their surroundings, but an extended region across the galaxy disk. So this is diffuse ionized gas that you see, which is clearly at some levels spatially correlated with these sites of star formation, but extends out to much, much larger sort of few kiloparsec scales across the disk. So all of these different components in the ISM are coexisting and sort of acting to regulate and trace the different changes that are happening in the galaxy and the star formation cycle. So in this life cycle of baryons, then you start out with some amount of atomic gas. It has to collapse into a denser form that can then further collapse to form stars. These stars then sort of live their lives, feeding back into the surrounding environment through winds and ultimately maybe through supernova explosions if they're massive enough. And this whole cycle can begin again. So in particular, the ionized phase of the ISM is tracing crucially this feedback phase, right? Where you're seeing the impact of those young massive stars on their surroundings and then their impact throughout their life and at the end of their life as supernovae. So to give you a little bit of a more detailed overview of these different ionizing sources in the disk, we'll start with a cartoon picture so we can look at the different mechanisms that are acting across the disk. In the centers of galaxies, there can be AGN that can be driving shocks and winds. Also centrally concentrated, there can be sort of central starbursting rings that are similarly driving shocks and winds and outflows. Throughout the disk, there can be H2 regions. These are regions where the O and B type massive stars are photoionizing their surroundings. Those generally are spread throughout the disk, but tend to be concentrated into sort of spiral structures. Supernova remnants can also be found as shock ionizing their local surroundings. And finally, planetary nebulae are also present, tracing an older population that's again an older evolved stellar population that's ionizing sort of local gas. And in a sort of broad sense, in addition to these sort of sites of particularly enhanced ionization, you can also have contributions from sort of the bulk older stellar population where some types of sort of old hot post-AGB stars, these so-called homes, hot evolved massive stars, these can also contribute at a low level to the ionization actually seen across the disk. So all these different mechanisms are acting in concert across the disk of a galaxy. And they're all contributing in different ways to the evolution of the galaxy, right? And tracing different aspects of feedback processes. So in particular, the sort of centralized AGN starburst is thought of as associated with quenching potentially within galaxies. The H2 regions can contribute radiation pressure and winds to sort of pre-clear some of the material before supernova remnants go off. This in simulations has been suggested to be very important as a sort of important early mechanism. Supernova, though, themselves contribute, of course, an enormous amount of mechanical feedback, as well as in metal enrichment to the surrounding ISM. And as I said, these sort of older evolved stars are also contributing at a pervasive low level to the ionization in a disk. So how do we learn about these different ionizing sources? How do we characterize them? So you may remember from Astro 101, maybe you saw these diagrams. These are looking at combinations of emission line ratios. The typical combinations are close in wavelength, so you don't have to worry too much about dust reddening and extinction. So this is the oxygen 3 to H beta as a function of nitrogen 2 to H alpha, or as a function of sulfur 2 to H alpha. And these diagnostic diagrams, if you take a single spectrum integrated across a large area of a galaxy, as was done with SDSS in its earlier phases, then you see that there's a certain regions in this diagram become populated. There's a clear sequence traced by regions that are consistent with photoionization, traced by basically H2 region photoionization. AGN contribute harder ionization and move basically the line ratios into a different parameter space on these diagrams. In addition to what we associate with sort of direct AGN excitation, we also see at perhaps a slightly lower level what's been called liner emission. This is low ionization nuclear emission line regions, which are seen in a number of galaxies. They seem to be not completely consistent with AGN excitation. And in fact, one of the really interesting results that we've had as we've moved from studies with a single spectrum from each galaxy to studies now where we can resolve galaxy disks. This is now early results from the MANGA survey, where we have each point on this diagram is kiloparsec scale measured within a galaxy. And we start to see that this parameter space is very similarly populated in a lot of ways. The star forming sequence sort of remains about the same, but this sort of contribution from a harder ionizing source appears much more populated than you would get from just a central AGN contribution, suggesting that actually this sort of, and these the liner emission we had seen before is actually more general of a property within some of these galaxies, that you have in general low ionization happening across broader areas in the disks. So a lot of what we know about these different ionizing sources and their morphologies and the distribution across the disk can be learned by looking at these sorts of diagnostic line ratios. There are other sources of ionization, so shocks, in particular from supernova remnants, but also from galaxy interactions driving gas flows, or from AGNs. These can also move you in this sort of same parameter space out in towards this direction that was similarly populated by the AGN contribution. So here you're seeing for a number of shock models how in luminous infrared galaxies, again on these sort of kiloparsec scales, that for moving from very low shock fractions of 5% out to high fractions of 80% for relatively moderate shock velocities of 100 to 200 kilometers a second. Similarly, this region of parameter space can begin to be populated due to this shock contribution. So all of these diagnostics are powerful tools for understanding the different ionizing sources in the disk and how they're impacting the gas around them. For a lot of my talk, I will actually be focusing on H2 regions in particular, and then radiation pressure, the winds, and their relation to star formation and metallicity. So H2 regions are sort of the bubble of gas that's been photoionized by the OB stars. They are particularly strongly detected in H-alpha emission. They're typically expected from models to be emitting for about 10 million years. So you're really seeing those youngest massive stars directly through their excitation of their surrounding gas. And in many ways, these H2 regions serve as interesting tracer particles. So, wherever you have that H2 region, it's basically illuminating and ionizing the surrounding ISM. And so while they're acting on these sort of very local, 10 to 100 parsec scales to illuminate their immediate surroundings, they're embedded within this extended gas disk, right? The H1 and the CO. So we have to keep in mind that these are living in this sort of multi-phase environment, multi-phase gas environment, and they're serving as tracer particles because you happen by wherever those massive stars formed to learn something about the gas properties in the neighborhood of that star forming region. Now for H2 regions in particular, we are often trying to learn about the physical conditions in the gas, in particular things like the electron density or the temperature. A lot of my talk, I'll talk about the H2 region, the metallicities that we can measure there, and the ionization parameters. So for example, here, if I show you again one of these line ratios, this is an N2 to H alpha as a function of gas phase oxygen abundance, the metallicity in the gas, that you can see for some of these ratios, they have a very clear sensitivity to changes in metallicity. So you have a diagnostic that you can use to understand something about the gas phase metallicity. However, some of these diagnostics have secondary dependencies on other parameters, in particular on the ionization parameter. So the ionization parameter is a ratio of the ionizing photon flux to the surrounding gas density over sort of that Stromgren sphere that's being photoionized. So this ionization parameter here now in color adds a secondary dependence to our understanding of these line ratios, but with a multiple lines observed, we can start to break some of these degeneracies. For example, this is another line ratio, sulfur 3 to sulfur 2, which has a very clear dependence on ionization parameter with actually very little dependence on changes in metallicity. So by using combinations of these line ratios, we can develop actually very clean prescriptions to try and constrain very, very accurately changes in the H2 region metallicities. So in my talk, I'd like to give you a little bit of overview of some of the results that we've had recently, focusing on first the chemical abundance variations we see in nearby galaxies. I'll show some very early results relating the ionized ISM directly to the stellar sources that we can see. And then if I have time, I'll talk about feedback and molecular cloud dissolution that we're trying to quantitatively constrain. So all the work that I've been doing has been part of the PHANGS collaboration. We're focused on understanding the interplay of the small scale physics of gas and star formation with galactic structure and galaxy evolution. This is a really large collaboration all across the world. And our work so far has focused on detailed study of main sequence star-forming galaxies. Our sort of core sample is about almost 100 galaxies. These are selected to be relatively face-on so that we can isolate individual star-forming regions near enough within about 20 megaparsecs so that the sort of, ground-based 1 arcsecond achievable resolution is about 50 parsec scales. And they're all selected to be on the main sequence of star formation. Oh, and they're southern, so we can see them with ALMA and MUSE and a number of other new instruments that we wanted to take advantage of. So we've been amassing data basically on this sample of galaxies with ALMA. We're trying to resolve the fundamental star forming units across the wavelength range. So with ALMA, we're tracing the individual molecular clouds, resolving and isolating those. With MUSE, this is an optical spectrograph on the VLT, we're picking out individual H2 regions. And with HST, we can identify and characterize individual star clusters and stellar associations. So these different observatories, these different telescopes are tracing different phases, again, in this life cycle of baryons. And so from our master sample observed with ALMA of, this must actually be a higher number by now, almost 100 galaxies, about 40 of them, about half of them were observed with HST, and about half of those, about 20, were observed with MUSE on the VLT. And this sample of 19 has also been approved for JWST Treasury program, so we'll be able to trace that early embedded phase of star formation as well. So just to give you some pretty pictures and a beautiful overview of the data that we have. So from our ALMA observations, we have amazing detailed CO intensity maps and maps of the gas kinematics. We have catalogs of individual GMCs. There's been a public data release for actually all of our data products. So if you want to go and download any of this and look at it and play with it, it is all publicly available for you. From HST, we also have these amazing, spectacular images tracing the different star-forming clusters. In particular, we observed with this near UV band so that we could see those youngest clusters and isolate them and constrain properties for the clusters like their mass and their age. And if we overlay in this image the ALMA emission in this galaxy, you can see how beautifully these two are completing the picture, right, of the cold dust here, seen in red, traced in by the molecular gas, with where you see those dust lanes in the HST image. So the synergies that are possible between these data sets are really amazing. So we're right now looking at ways to improve, for example, our SED fitting in the HST bands that we have by combining sort of ancillary data we have from, for example, the ALMA data or from the MUSE data where we have constraints on the dust reddening from the Balmer lines as well. From the VLT, we've been making use of observations by MUSE. So this is an integral field spectrograph. So that means in this beautiful image, we actually observed this with 3x4, 12 total pointings with MUSE because it has about a 1 arc-minute field of view. And each of these pixels in this image is actually an optical spectrum. And so if I step through the spectral channels, you'll see that we have not just continuum light, we have spectral lines from H beta, O1, H alpha, all the way out into the red. And so these are tracing a full suite of really crucial mission line diagnostics for us to parameterize the different ionizing sources in the ISM at a spectral resolution of about 2000 so that we can also constrain to some degree the kinematics in the gas. And all of this is done with this amazing high spatial resolution, sort of 1 arc-second scales is about 50 parsecs. So we can isolate individual star-forming H2 regions from their surroundings. We can still go deep enough. We see the diffuse ionized gas that's extending from these regions. And we can talk about characterizing the different sources. So in this 3-color image, this is actually a combination of 3 different emission lines. We can see how differences in color are actually indicating differences in ionization mechanisms across these different regions. This is an amazing multi-purpose data set. So as I said, we have the stellar continuum emission detected such that we can actually model and measure the stellar mass surface density at very high spatial resolution. We have the emission lines to trace the ionized component of the gas. We can see from, for example, the broadening in supernova remnants that the kinematics in the gas can differ. We see differences in line strength. So for example, the AGN has a very strong nitrogen 2 contribution compared to H alpha. So we can directly trace all of these changes in the ionizing sources. We have kinematic constraints on both the gas and the stars to do sort of dynamical modeling and trace the gravitational potential in the disks. And in combination with the HST data and the ALMA data, we can also see directly in some galaxies spatial offsets tracing sort of this star forming sequence as the molecular gas has to have collapsed to form the stars that were young enough to photoionize their surroundings and then age as they come off the spiral arm. So we can trace directly.
Can I interrupt?
Yeah.
I just wanted to ask, sorry if you already said it. Are there any mergers in your sample? Like
so only by accident, I think. We didn't select against that, but there's very few within about 20 megaparsecs. So I know one of the galaxies, 3627, is interacting. I don't think any of them, they're all falling along the star forming main sequence. So I think anything that was too big of a starburst mess, we would not have selected. Yeah.
Cool. Okay, thank you.
So here's a few images of some of the galaxies in our sample. Yeah, so I think 4254 is also interacting, but with a small, maybe with a small companion. So there's nothing really big, you know, like antennae, like a big mess. They all look like relatively, they all look very cleanly like spiral disks, but with different morphologies in details, right? So some of them have very strong bars and widely separated spiral arms, while others are much more flocculent or have much clearer sort of ring structures and central star-bursting rings. There's another set. So some of them have AGN contributions, which you can clearly see, and the really strong O3 contribution. So we have this wide variety of different environments traced within all of these galaxies. And I should also point out that we've had just this last summer, our first public data release, which is now available on the ESO Science portal. So you can, again, go download these beautiful images, play with them, do science with them. So the project that I was focusing on first with this data set was to look for chemical abundance variations. So again, here's one of these beautiful galaxies, NGC 4254. And if we shift from this optical view reconstructed from the MUSE data to a view of the H alpha, the ionized gas that's been ionized mainly by these H2 regions, we can see the sort of amazing number statistics we're starting to collect in terms of picking out these individual H2 regions. And for each of these pixels in this map, we have a spectrum. So in the past for this galaxy, the number of metallicity measurements as a function of radius was on the order of 10, 20. With our MUSE data, now we've moved to a regime where we have thousands of spectra, spatially resolved H2 regions where we can measure using strongline methods, the metallicity as a function of radius. And so then we can go back to our image and move away from this view of just looking at radial gradients and metallicity to looking at two-dimensional spatial distributions of the metallicity across the disk. So the first thing you'll clearly see is again, this radial trend that the centers of galaxies tend to be more metal enriched compared to the outskirts. So we, to further our analysis, we actually fit and remove that radial trend in metallicity to look at the residuals in the metallicity distribution relative to the radial gradient. So that's what I call delta OH in these plots. And what we see is that we can do this sort of analysis looking at, again, thousands, hundreds to thousands of H2 regions per galaxy. And across our whole sample of 19 galaxies, we actually have hundreds of regions, about 1,000 regions with auroral line detections where you can more accurately go and measure the metallicities using temperature sensitive indicators. So using these sorts of maps, in a preliminary sample of 8 of the galaxies, we first looked at the metallicity variations across the disk and found that about half of them showed significant azimuthal variations, in many cases correlating with spiral arm positions in the disks. But often it was not in a symmetric way. So we would see this on one arm, but not the other. So this is really a new view of the metal distribution in gas disks. And in fact, there's been a very recent paper from our group just a month or two ago, where one of the postdocs here at MPIA, Tom Williams, has applied a Gaussian process regression to the metallicities in order to derive interpolated metallicity maps. So you can see really how the spiral arm here is tracing a change in the metallicity across the galaxy. So these sorts of interpolated maps are really powerful because often where you see the H2 regions are not co-spatial with where you see the gas because you have this sort of time evolution. So being able to interpolate across the disk is going to be really powerful for our future studies.
So for these maps, I'm sorry if I missed. These are from the strong lines, or these are from? Okay.
These are still from the strong lines. Yep. So the next slide, I try to convince you that what we see in the strong lines, we believe,
Okay.
Because we see some of it with the aurora lines. Yeah. So this was one of the first galaxies where we see a very strong trend in metallicity distribution across the spiral arm. So if you see in the optical image, the spiral arm is sort of traced out here. And in the H2 region distribution, you see a ridge of H2 regions from strongline methods that have very high metallicities, followed by, because this is inside co-rotation, this is the trailing side of the arm, so followed by H2 regions with decreased metallicities relative to that spiral arm. And so I don't go into a lot of detail here in this talk about the differences and how we measure metallicities. Suffice to say that when we make these measurements, we are typically relying on the brightest lines, which means we make certain assumptions about the density in the gas and in particular the temperature in the gas. But there are lines that are much fainter where we can actually directly measure the temperature of the gas to improve our estimates of the metallicity. And many of those are detected by MUSE. So here you can see, again, this is the spiral arm trace from ALMA. So in very good agreement with where we see this ridge of enhanced metallicities. And so we tried looking at these temperature sensitive auroral lines to confirm that temperature variations support these abundance variations we're seeing in the strong line methods. So here now we're breaking up the different H2 regions by temperature. The lowest temperature regions are typically associated with higher metallicities because the metals are more efficient at cooling. And then we can compare that sequentially with the warmer and warmer electron temperatures. And we see that this shows exactly the same trend as we had identified from the strong line methods. So the ridge along the spiral arm is sampled with electron temperatures that are much lower than on the trailing side of this arm. So this gives us a lot of confidence that the abundance variations we're tracing with the strong lines are fairly accurate and reflect actual changes in metallicity.
I have another question, Kathryn.
Yeah.
Is this something that can or has been done in the Milky Way, where you can kind of see this trailing side of a spiral arm, also based on the intensity of these types of lines, or is it not feasible in our own galaxy?
So the Milky Way is hard because I think projection effects make it very, very difficult to distinguish where things are in great detail across the disk. I know this has changed to some degree now with, Gaia putting tying distances now to objects much more precisely. But I think still, the papers I've seen about abundance variations in the Milky Way, they tend to talk very broadly in terms of like quadrants.
Because the distance is really the limiting.
The distance is really challenging, yeah. But now, with telescopes like the VLT, we can actually start to do this across large samples of H2 regions. We're also, so there's the goal is to try to do this in nearby galaxies at great levels of detail. Yeah.
This is really, really cool when you talk about why you think this is happening. So you have the gas. Is it just because you think that's where gas is and that's where they make more stars and they enriched the area more, or what do you think is kind of?
Yeah. So right. So as I was saying about the H2 region as a tracer particle, right? The basically your H2 region is illuminating the gas that was already there. We don't think that there shouldn't be a significant enough amount of material during the course of those lifetimes of those massive stars enriching anything that the effects we see are much larger than you would expect just from sort of pollution within the lifetime of one H2 region. So what we think, there's a couple of models for this. The one that, so far we've favored, I'll mention later towards the end, is that later in the talk a bit, is that you have some parcels of gas that are basically pre-enriched by a previous generation of star formation, or perhaps by a sort of extended continuous history of star formation in that area. We estimated that the sort of one previous generation of stars might be able to enrich the gas to the level that we're seeing. So it doesn't take a lot of pre-enrichment, but it would have to be sort of a previous generation of stars. So then, combined with this dynamics of the gas through the disk, you basically need that pre-enrichment to happen while you're moving through the inner arm. And then along the spiral arm, you get this triggering of a whole bunch of star formation, so you can illuminate and see all those enriched particles of gas. Once you pass through the spiral arm, you get a lot of turbulence, which might introduce material from larger scales, which is less enriched, so that on the trailing side of the arm, you see lower levels of enrichment. So that's one idea for how this happens. The other idea is that you get radial flows driven by a spiral structure in a galaxy. And so that could also be, because you have radial gradients, then if you have radial flows, you could end up with material which is basically more enriched along, I forget which side of the spiral arm, either the leading or the trailing side. So you get the flows preferentially on one side of the arm. So you could see these enrichment patterns because of that as well. So we need basically more data to try to confirm which of these pictures is more accurate.
I'm thinking also about our work, which is using H2 regions near supernovae or at the new supernova sites to try to probe the natal metallicity of the stars or the stellar populations, kind of similar to what gave rise to supernova. But the kind of numbers you show, they're really, these variations are very small, right? You said like 0.5 to 0.2.
Yeah, that's
so
right.
That's when we measure things in extragalactic systems, that's our statistical error bar is like bigger than that. So so in some ways, I guess it would be washed out when we're trying to do that, and then would be kind of semi-probing the area and the natal metallicity, unless there's these very strong radial flows, because that's the worry, right? If they have strong radial flows, then the stars moved away from the H2 region side.
Yep, that's right. Yeah, so that's right. It's hard to disentangle some of those effects, indeed. So one saving grace might be that so while we see these variations as musically, if you look sort of on these large 3 kiloparsec scales, things look fairly they might average out to 0, but on sort of sub-kiloparsec scales, there's actually quite some homogeneity that we see on within the H2 region. So like the blue regions all cluster together, the red regions tend to cluster together. So to some degree, there is quite a lot of homogeneity, we think, in the ISM on sort of these sub-kiloparsec scales, which I think would help this effort to use the nearby H2 regions to trace the metallicity of your stellar progenitors. So after we had made these maps, this feature was really apparent. So we tried to quantify basically the level of homogeneity that we were seeing. And so one way we tried to do that was by dropping, by looking at different scales around any given H2 region and looking at the scatter in the metallicities that we were seeing, again, as a function of scale across all the different H2 regions in the galaxy. So these different colored lines are different galaxies. And so what you see for all of them is that on sort of large, 3 kiloparsec scales, you reach some sort of a plateau of systematic level of scatter. But as you go to these sub-kiloparsec scales, the scatter goes down, the metallicity becomes more homogeneous. And in fact, the systematics from the strong-line metallicity calibration we're using, we actually don't expect to ever get more precise than basically this 0.02 to 0.03 deck level. So we're hitting the floor of the sensitivity of the method. And if we normalize all of these galaxies, given they have these sort of systematic offsets, then we see a very consistent shape in between them all. And we compare that with the null hypothesis in gray. So here we have shuffled all the measurements of metallicity across all the disks and repeated the analysis. And so we find a significant difference in all cases on these small scales, this increase in homogeneity. These galaxies are sorted here by stellar mass. So the reddish colors are the lowest mass and the purplish blue are the highest mass. And we don't see any strong, clear trends by mass in the galaxy that sort of account for these systematic differences in the overall scatter, or we don't see any changes in the trends here. Another way to try to quantify this is by looking at a 2-point correlation function as a function of scale in all of these galaxies. And so here you see every H2 region correlates perfectly with itself. And as you move to larger and larger scales, then the correlation actually decreases. But again, what you see in comparison with the null hypothesis, where we shuffled all of the metallicities, as we see significant differences in these 2-point correlation functions out to significantly larger scales, to very large scales, sort of a few kiloparsec scales in all these galaxies. We compared this to analytic model in the literature from Krumholtz and Ting, which they parameterized for 2 fiducial stellar mass regimes, so this normal spiral galaxy and for a dwarf galaxy. And we find very good qualitative agreement with the sort of shapes of their models, but we don't see really any change with mass as their model might predict. So to come up with it.
The null hypothesis is that there's a completely uncorrelated dispersion from H2 region to H2 region.
Yes, yes.
Okay. All right, thanks.
Yeah. So to try to quantify the sort of correlation scale from this measure, we set a sort of a correlation scale of 30% and measured then at this 30% level how what scale we reach that in for each of the galaxies. And we did this not just globally, but for 2 kiloparsec wide rings within the galaxies. And so what we found is this 30% correlation scale shows no trends with radius in the galaxies. It shows a weak correlation with the star formation rate, surface density in those different rings. But the strongest correlations we actually find are with the gas surface, the gas velocity dispersion. So here, this is seen in the ionized gas, and this is seen in the molecular gas. And because the molecular gas tends to have a much lower scale height, if you actually try to account for the difference in scale height between the molecular gas and the ionized gas, you actually find very good agreement between these 2 trends. So this suggests that the turbulence in the gas is partly responsible for driving these correlations that we're seeing. So one last analysis we also looked at was to look individually at only those H2 regions that seem to have reduced abundances compared to the radial gradient, and repeat this analysis looking at the scatter in the metallicities as a function of scale, where we can recover again the same increase of homogeneity on small scales. When we do this, though, for the H2 regions with enhanced abundances, this correlation goes away completely. So that suggests that actually what we're seeing in terms of this increased homogeneity is it's an effective dilution rather than pollution. So it's sort of a mixing of more pristine material from these larger scales, which is causing this homogeneity across kiloparsec scales. So as I was sort of describing before, the cartoon picture that we are favoring at the moment is that you have some sort of localized enrichment as parcel of gas moves through the inner arm. You hit the spiral arm that triggers a bunch of star forming regions to form. You see all that enriched material, but then the turbulent mixing driven by the spiral arm passage or by the increase in star formation rate is responsible then for bringing in less enriched material, maybe from larger areas in the disk or from larger scale heights, and then decreasing the abundances. So I'm going to move on to a slightly different topic. I want to talk about some of the projects that members of my group have been working on relating the ionized ISM to stellar sources in the disks. So I showed before beautiful sort of HST, PHANGS HST images that we have. If we combine those with what we have from MUSE in red with the H alpha, with where we see those young massive stars directly from their near UV emission, you can see how nicely the correspondence is along the spiral arms. If we zoom in, then we can see again how these sort of young star forming regions are surrounded by the ionization that they're causing, right? And from the HST data, we have a number of derived stellar properties. We have catalogs, including things like the mass of the ionizing cluster or stellar association, the age and the reddening that you would measure just from the HST data. And so my student, Fabian Scheuermann, has been looking at combining these catalogs of the associations, the stellar associations traced from HST, with the catalogs of the nebulae traced by MUSE and identified by MUSE. And so he tries to pick out right now the nicest, cleanest selection where you have a nice one-to-one match and, you know, the stars fill pretty nicely, the ionized nebula that you see. There's a significant difference in the angular resolution between HST and MUSE. But of course, you know, we do the best we can. It is a little depressing when you look at the few H-alpha, HST narrowband images that we have, how much substructure is lost even when we have these sort of 50 parsec scales. But these sort of one-to-one correspondences are really quite convincing. And so one of the cleanest results we have is that you can see, if you look at the reddening that you would derive from the stellar SED fits, compare it to the reddening you would get from comparing the H-alpha and H-beta Balmer lines, then for the youngest clusters, they fall really nicely along the one-to-one relation. And as you actually move towards older clusters, they start to move off this line. So perhaps those clusters become a little less embedded in their natal birth cloud, and you start to see that the two do not actually correlate so well. So the project that he's been working on is to try and pin sort of an age sequence, an evolutionary sequence, to a lot of the traces we have from MUSE. So we can look at things like the equivalent width in H-alpha, the ionization parameter Q, or this change in metallicity as a function of age. And we see very weak trends. I mean, some of these, you know, from Starburst 99 stellar population modeling, you expect things like H-alpha equivalent widths to correlate quite strongly with changes in age. So we've been struggling a little bit to understand why these correlations don't appear as convincingly as we expected. But what's also interesting is that, you know, while the correlations with the age we derive from HST aren't always, they're present, but they're not as convincing as we hoped. We see very tantalizing and interesting correlations between equivalent width of H-alpha, which we think of as an age tracer, and parameters like the ionization parameter and the metallicity. So right now he's working to try and understand, are these truly correlations with age? Why don't we see this with the ages from HST? If they're not correlations with age, then what's going on here? And so one of the things he's been exploring, given that we know what the ionizing star cluster is, we can compare the predicted ionizing flux, given that stellar cluster age and mass, with the observed ionizing flux. And in particular, we know, of course, by looking at detailed images, that any individual H2 region isn't a perfect bubble. There are channels through which ionizing radiation can escape. And so there's some sort of escape fraction is expected in these regions. And so what he's been finding is that escape fractions of on the order of 70% appear typical for the H2 regions in our sample, but they don't show any additional dependencies on parameters like the ionization parameter. So we're still working to understand what this tells us about this age sequence and this age progression in the H2 regions. So, but it's an amazing synergy of these data sets. Yep.
Yeah. Wow. One question, the observed Q here is observed, meaning inferred from the line ratios.
Yes.
The lines, from the optical lines.
Yes.
But also the equivalent width is the continuum. The continuum you think is dominated by the stars in your cluster?
Yeah, it's a good question. We hope so, but it's true that there's, of course, they're sitting in a big stellar disk, so we don't know for sure. And in fact, I mean, we do the stellar population modeling of the spectra at the position, and we find right now there's another student in the group, Ismail Pesa, who's really struggling because the stellar population models don't really accurately recover the spectra that we are seeing And this seems to be actually kind of a known issue in the stellar population modeling community, that the spectra don't match very well with the youngest stellar populations. So we're working on improving our understanding of that. But I don't have a great answer for you right now, but this is definitely something we worry about.
So early on, you had the nice plots of UV, right, and H alpha. And so people use those for star formation indicators, right? This is, if I remember correctly, like the H alpha tells you kind of the different, ages, right? H alpha versus near UV. So have you, are there any implications for that kind of, because that's a huge area of research, like star formation indicators for galaxies, also different methods, different redshifts, right? H alpha goes out of the observed waveband at larger redshifts and so forth. So are there any implications for that, which star formation indicators one should use, or for which?
So there's another panel in this that got cut in making the talk, which was showing H alpha to FUV, because we have astrosat imaging for a number of these galaxies. So this is really expected to trace sort of directly the young stellar population that's there. And it similarly shows confusing lacks of strong correlations with age. So we're still working to understand how well the models are doing at recovering the lines, these ratios, these diagnostic ratios, but also if there's problems maybe with any of our SED modeling or anything like that. All right, let's see. Another exciting project that's being led by my postdoc, Oleg Egovrov, is to look for giant super bubbles within some of these galaxies. So these are, for example, if you zoom in here, regions which actually have decreased H alpha intensity, but increased velocity dispersion in the ionized gas. And you can compare that with the individual stellar associations identified from HST to try to correlate the mechanical energy input from those clusters with the kinetic energy that we see in the turbulence in the gas. And what he finds is, as a function of the sulfur 2 to H alpha ratio, which is tracing changes in shock, such that these sort of yellow points are expected to actually be dominated maybe by supernova remnants, we see a nice correlation for the regions that are presumably more photoionized, and that as you have supernova contributions coming in, they actually begin to disrupt this correlation and move your regions off of these sort of efficiencies of reasonable ranges of efficiencies. All right, I think I don't have time to go back into the molecular cloud topics. So I'm gonna spend the last few minutes here talking about what's next. So ideally, to understand a lot of what's happening in these H2 regions, 50 parsecs, you're not resolving really the H2 region, you're isolating it from the surroundings. So if you want to resolve the internal structure of the H2 regions to really see how the photoionization is affecting the different layers of the gas, you need much higher resolution, sort of less than 10 parsec scales, means you have to look at really nearby targets. But we also want to connect the small scale physics to the large scales, right? As I showed in terms of the metallicity enrichment in the disk. So that means you need a wide area covered and you need dedicated surveys. And so this is the sort of thing that SDSS excels in, and one of the projects that we're pushing in SDSS 5. So just to actually give you another look at how difficult this problem is. So this is IC342. This is a nearby galaxy that's only 3 megaparsecs away. It's probably one of the most massive nearby galaxies. It's, sort of 10 to the 10, but it's behind the Milky Way, so it's not that well studied. And it spreads across a huge area in the sky, right? So this is 5 arc minutes across. This is sampling just the central 5 kiloparsecs. The spiral arms, of course, go much farther out in the disk. So surveying a galaxy like this with something like MUSE is really hard. It takes a huge amount of time. But we had an ancillary program actually with Manga to try to do this. And just to demonstrate how difficult this is, it took 49 plates from Manga, which is over 340 IFU bundles put together to form this image cut out from the center of the galaxy. So again, each of these pixels in this image, which is actually very blurry, it should be better resolution. Each of these pixels is an optical spectrum. So doing a detailed survey of nearby galaxies, which are such huge across the sky, is really, really challenging. So, you can try to do this. Manga itself was targeting more distant galaxies in sort of kiloparsec scales. You can do that for large surveys with thousands of galaxies. PHANGS were taking the approach of targeting, tens to maybe 100 galaxies at sort of these really crucial 50 parsec scales. But if we want to get to this sort of 10 parsec or parsec scales, we really have to look within the local group. And so that's what the program, the Local Volume Mapper, is aiming to do. So LVM wants to target, I actually don't have that on this slide. We want to target the Magellanic Clouds at 10 parsec scales, and the Milky Way, depending on the distance, will be sort of parsec to subparsec scales. And to do that, we have to survey huge areas of the sky. So the idea is you take DESI spectrographs with R of about 4,000. That's reasonably good spectral resolution covering the full optical range. You take 3 of these spectrographs and 1,800 fibers that are fed by a tiny 16 centimeter telescope. So that's what gives you this wide area coverage on the sky in order to do these surveys. We have 2 simultaneous sky telescopes, which are pointing to either side of your science object, because the science object, if it's the Milky Way, is filling almost all of your sky and certainly all of your field of view. And then we have an additional flux calibration telescope to sort of simultaneously be observing a whole stream of stars. And so we plan then to survey the LMC and SMC completely, and the Milky Way across the southern hemisphere. We are still planning for a northern hemisphere survey, but that's been delayed pending the successful start of the southern hemisphere. So to do this sort of amazing survey area requires a huge field of view. So the science IFU bundle will basically have a field of view the size of the full moon. And as I said, we'll cover the LMC, the SMC, the bulk of the plane in the south, Orion, of course, in great detail, and then some grid across the sky to trace the extended sort of diffuse ionized gas in our own Milky Way. So just to give an example of why this is so exciting, Orion is our nearest star-forming region. It's, of course, so nearby that, individual spaxels in LVM will be covering 0.1 parsecs. And within these sort of Milky Way, local group star-forming galaxies, individual stars and stellar sources have been studied in amazing detail. So already from apogee, there's been quite a number of stars in the Orion region here marked in yellow that have been studied. That means we'll have effective temperature, the luminosity, the stellar abundances, ionizing photon flux for each of these stars. And if we pixelate this image to the resolution we'll have with LBM, you can see how we can do this amazing matching then of the gas properties, the temperature, the density, the kinematics, the abundances, mapped at the positions of the stars and around in their surroundings. So you can really trace in detail the interactions between the stars and the ISM. So this is a really exciting next step for our studies of the ionized ISM. And you should look for us to hopefully get on Sky by the end of next year and start taking data. So that brings me to my summary slide. I hope I've shown you a little bit about why the ionized ISM is so interesting and what it can tell us about galaxy evolution. I showed you a little bit about the chemical abundance variations and sort of azimuthal variations we see, but also the kiloparsec scale homogeneity that's indicative of efficient mixing. I showed you how we're starting to relate the ionized ISM to the stellar sources, and we're trying to anchor the timeline for the star formation process. And I unfortunately didn't get a chance to talk about the feedback and molecular cloud dissolution that we're starting to constrain. So thank you for your attention, and I'm happy to take questions.
Rowdy here.
Thank you very much, Kathryn. Let's see if anyone has their hand up. Yeah, Mike, you can go ahead.
Yeah, I love this stuff. There's a lot of questions I have, but I think my main one is for this story you have about the chemical abundance variations around the spiral arms. Is there a sort of hydrodynamic simulation basis for that story? Is that even possible to check with, with simulations, so they make a prediction about what you should see?
Yeah. Yes. So I just refereed a paper that I tried to do this with some hydrodynamic simulations, but it's true that, so I think this level of variation in the gas phase abundances is there's a level of okay, so there's two things to say. So, to first order, actually the radial gradients are dominating, right? So the variations we're seeing are somewhat small. So this is sort of a new development that we can see this with the sort of level of precision that we do. So I think now there are groups exactly that are starting to look at this in simulations and see if it can be reproduced or explained and tested, which of these sorts of mechanisms might be causing the effects we see. But there's no answer there yet.
Yeah, I mean, it just seems like it's such a, it is such a detailed thing that it might be very informative to the way that, the simulations get like some big things about the galaxies right, but they also have to get all these little things right.
Yeah.
And so, and they can get the big things right in various ways. So it's these things that will allow you to tell the difference.
Yep, I think so too. And actually, I mean, a lot of my thesis work, I was interested also in sort of flows of gas onto galaxies, right? So we get, even I get, buried in the details of these star forming regions, but it's also interesting to keep in mind the sort of larger picture. A lot of these galaxies, if you look in H1, they have these huge extended like tails and things. So there's clearly material that could be infalling and also contributing maybe to some of these sort of variations you see in the abundance. So I think it's an interesting test for these simulations, especially even in the cosmological context, to see that they're getting the right level of metal abundances and variations. Yeah.
Cool. Do we have any questions from 940?
Yeah, so one thing that I seem to remember from a few surveys like Khalifa was that perhaps there might not be kind of these radial metallicity gradients as clearly as we thought when we just had long slit. And in some your work, you took out that kind of general metallicity gradient. That's what you have, like the delta, right? So, but I guess, I mean, it's smaller sample that you have, but you do find that there are radial metallicity gradients.
Yes, there definitely are. Yeah, so I think a lot of so things like Khalifa, they have the advantage of large number statistics on galaxies, right? We only have 20. They're not covering a huge range in stellar mass. We wanted things to be, relatively massive, metal rich, so that we see them in ALMA with the molecular gas. So we're not really probing a super wide range of parameter space. But yeah, we definitely see gradients, and the galaxies where we don't see gradients all have really strong bars, like really strong stellar bars. So it's been some interesting papers in the past which claimed, from I think surveys like, Khalifa, that, stellar bars don't change the metallicity gradient. I mean, okay, this is a small sample of like 19 galaxies, but the ones with strong bars, you don't see any metallicity gradient in the center. So it seems to me quite clear. That's, some of these conclusions from the larger samples maybe it's the spatial scales they're looking at, that they're covering, you know, a single fiber is maybe a kiloparsec or a few kiloparsecs. That means you're mixing H2 regions. It means you're also, there's diffuse ionized gas that are influencing your sort of line ratios, and your modeling, your, you know, modeling of the metallicities may not be correct. So there's a lot of other, you know, concerns that I would have in trying to make sure that those results are robust. But I mean, those people know what they're doing. I just think that with this high resolution view, you can really pinpoint these metallicities. So it's important to test those claims, definitely.
Well, I had one question too. I was wondering if there's anything to be done based on the morphology of the H2 regions alone. So I know you were talking about spatial resolution, but I was just thinking back to that spiral arm, and you could see a metallicity gradient trailing behind the arm, but you could also see just the disturbance in the way they appear. And I think that's kind of inferred from the intensity lines, right? So it's not a direct morphology, but has anyone looked into just a morphological study at all?
Yeah, so that is, yeah, I think with our physical resolution, it's a bit challenging to do that. We are proposing, we have proposed a number of times to try to get HST, H-alpha narrowband imaging, because I think that would be the right approach to really pinpoint the morphologies of these H2 regions and the sizes. I mean, there's a number of parameters, you know, if you want to infer things like the radiation pressure in the H2 region, then you need to know the size very accurately. And what we have is basically upper limits. So it's really hard to put strong constraints on that. And if you look at the HST images when we do have them, a lot of these like have really disturbed morphologies. They show these bubbles that are, you know, open and broken and complicated, like clusters that in MUSE we only see as one region. So we need the higher resolution data to do that in detail. But it's definitely something we want to do. Yeah.
Cool. I'll see if there are any more questions. Just a heads up, I'm muted 9:40. So if you want to say something, you have to go up and unmute, I think. But I don't think I see any more questions on Zoom. So let's thank Kathryn again. And I thought that was a very incredible talk and amazingly beautiful data. Very impressive. So thank you very much, Kathryn. Have a great evening.
Thanks. You have a good day. And,
thank you.
Bye.
Bye, everyone.